The next step is to assess the sensitivity. That is, how do the conclusions of your study, the results of your simulation, depend on the parameters that you're putting into your simulation? If your conclusion is robust, that means it doesn't change much to things that you're uncertain about, you have low sensitivity. That's a good thing. You can have confidence in your results. By contrast, if your results are very sensitive to unknowns in your simulation, it's hard to have confidence in your result, and you might not have a solid scientific study. So to understand sensitivity, you can ask the following questions. What inputs have the highest variability or uncertainty? What inputs have the biggest effect on your research question? And what input or modeling uncertainty change the answer to your research question? As I said, if things make a big difference to the answer to your research question and you're unsure about them, you have high sensitivity, and that can be quite challenging. So let me give you, going back to our specific example of how we tested simulations. One of the things that we did was we wanted to calculate the ankle moment, and we can do that in the simulation by summing the moments generated by the muscles that cross the ankle. So we sum the simulation results for the ankle. We can also perform inverse dynamics. And in inverse dynamics, we're computing the net moment as well. And we can compare the simulated moment to the inverse dynamics moment. We can also compare simulated powers. So here we have our muscle forces times their velocities, or the muscle moments times the angular velocity. And we can also compute that with inverse dynamics, where we estimate an angular velocity of the joint and a net muscle moment of the joint. We can compare those. So what we found was that in our analysis of our simulation, while we were answering our scientific question, was that the ankle moment and the ankle power were sensitive to tendon compliance. So what we did was a sensitivity study where we computed the ankle power for a variety of different tendon compliances or tendon stiffnesses. One where tendon stretched about 3% when the muscle was generating its maximum force, all the way up to 12% when it was generating maximum force. And what I'm plotting here is the net ankle power versus time from inverse dynamics and from our simulation with those different tendon compliance measures. And the one where it matched best was around 10% stretch. If we had used a lower compliance, a stiffer tendon, we didn't get a good match. So we had to adjust the model for analyzing the ankle muscles. We then needed to compare to experiments and other models, and this is a good process. Before we finish a scientific study, we are constantly comparing our simulation results to experimental results. So what do I mean? Does your simulation match experimental results? Your experimental data, other experimental data in the literature, independent models in simulation? All of these can either build or lose confidence in your simulation. And in which case, how much is good enough? How good does your model need to be? To do this, to test the accuracy of the simulation, we suggest testing with experimental data as comprehensively as you can. So what kind of comparisons could you make? You could compare your simulated joint kinematics to experimental joint kinematics. Just like we did in the last example, you could compare joint moments. How do your muscle-generated moments compare to inverse dynamics moments? You can also estimate ground reaction forces. In some simulations, we'll model contact between the foot and the ground and compute ground reaction forces, and you can compare that to the measured ground reaction forces. Comparing your muscle activations in the simulations to EMG is another good test. Now, you frequently will not have muscle forces estimated from experiments, but you may be able to get that from animal models, for example. Same with joint reaction forces. You might not have experimental data, but in some cases, there are rare cases where that has been measured. And when we care about joint reaction force, we'll compare our simulated joint reaction forces to experimental results. The next step is to make real-world predictions. We'll get to that in just a minute.